And so now it's my pleasure to introduce CS Rajan, who will be giving a lecture on non-commensurable isospectral locally symmetric spaces.
Can you hear? Yeah. So my thanks to the organizers, Sury, Rapinchuk, and people for the invitation to speak in this conference. And it's a great pleasure to speak in front of Gopal Prasad, who was my teacher when I was in my undergraduate days at TIFR. And we learned a lot. I think I remember Sury and myself, we gave a course of lectures on buildings to us, and that was very nice. So thanks for that. And so I'm going to talk about non-commensurable isospectral spaces in the locally symmetric case. So this is the examples of joint work with Sandeep Verma, who is in the audience. So let me say it's joint with Sandeep Verma. But before that, let me just give a small bit of introduction to the subjects. I hope I'll have sufficient time to do that. So what we have is that MG is a, so let's take a compact Riemannian manifold. And associated to that, you have a very nice, good operator, the Laplacian. This is a Laplacian operator, say acting on say functions. It has unbounded operator, but it's essentially self-adjoint. So you can talk about its spectrum. And since I'm assuming compact Riemannian, so you can look at the eigenspectrum. So the functions are all on smooth functions. F will be a smooth function on M by regularity and other things. So you can look at the multiplicity of the eigenvalues, and the eigenvalue set, you can, it's a kind of discrete set with, the multiplicities are finite, and you can say the spectrum of the manifold Mg is this collection of eigenvalues counted with multiplicity. Eigenvalues of Laplacian on the space of smooth functions. And so it's probably a problem arising from physics motivation, whether the spectrum determines the manifold, or whether if you know the spectrum, like for instance, if you are playing a drum or something, if you know the tones which are coming, can you figure out the shape of the drum, which was a question asked by Mark Katz. So with multiplicity, yeah, with multiplicity. I said it, but I didn't write it. Counted with multiplicity. Yeah. So question is whether the spectrum determines the manifold, and there are many examples where it was given. So the first example was due to Milner, where he worked with two lattices, which is E8 direction E8 in R16 and R16 by E16. These are some even unimodular, and suppose some positive definite or something comes out here. And it's a computation using that the theta functions are the same, and you get that these spaces are isospectral. This was the first example. Then there is much later in the 1980s, there's an example of Tsunada. So let me explain this example of Tsunada, which is that you take G as a finite group. Yeah, Tsunada's example was, I should say, Tsunada-Gassman. Gassman used this example to produce examples of number fields which have the same zeta function, but which are not conjugate. So what is the example? How do you produce them? So take G to be a finite group, and H1, H2 are two subgroups. Such that the regular representation of the spaces C of G mod H1 is isomorphic to the space C of G mod H2. Okay, I can put any field K out here, that if the regular representation of the group G on these spaces are isomorphic as G spaces. Okay, so that's a setting. Now, what? Suppose G acts on M as this thing, a compact Riemannian manifold, and H1 and H2 acts 6.3, or you can assume H1 acts 6.3. So then you can form the quotients. Then what? With respect to the induced metric, then this is a covering space M to M mod. So with the induced metric is isospectral. This is isospectral to M mod H2 G. But in cases where you can produce examples where H1 and H2 are non-conjugate inside G, which is not too difficult to do that, then you can see that in general, these spaces will not be isometric, especially if M is simply connected, if you take M to be simply connected. And the proof of this, so let me give a proof. So this was in a paper with Deependra Prasad, where it just follows. So the proof is uses naturality of Frobenius reciprocity. In the sense that if you have an operator like, so you take V is the space of smooth functions on M, and you have Laplacian acting on that, which is, so I'm assuming that G fixes the metric. Suppose G fixes metric, anyway, I'm taking the metric which is there. So the Laplace commutes with the action of G. Laplace commutes with action of G. And then you can, so you have to, the space C infinity of M mod H1 is isomorphic to the invariant functions. And what you have to see this, that Frobenius reciprocity gives an isomorphism of V of H1 as isomorphic to V tensor the G invariance. And the naturality will, so we have a map, the Laplacian of course will give you a map from V mod H1, but here you can substitute for V tensor C of G mod H2 and take the G invariance, and this gives us V of H2. So you can, saying that the G regular representations are isomorphic, you can shift the Laplacian. So there is an isomorphism. This isomorphism is natural with respect to all these operators. And so you get the proof of Sunada's theorem that these spaces are isospectral. Okay, so that gives you a proof of Sunada. So what happens is there are later examples constructed by Veneras of compact hyperbolic surfaces which are isospectral but not isometric. And see what, both in all these examples, whether it's Milner's or Sunada's or the Veneras example, it turns out that these manifolds are what are called commensurable. I'll come to Venera's example later. That will be the almost in the sense that they have a common finite cover. They have a common finite cover. So the question is, you know that the spaces are not isospectral. If you know that is, if you know that they are isospectral, you know that the spaces are not isometric. So then the next thing is whether they are commensurable. But of course, in the general context, there are probably continuous families of isospectral spaces which are not mutually isometric. So these commensurability questions have a negative answer in general. But what you can ask is what is in the context of locally symmetric spaces, Riemannian locally symmetric spaces. Venera's is before Sonata. Sonata is actually was led to it from looking at Venera's work. And of course, the Gassman example, which is 1930s. Gassman is 1930s. Yeah. Yeah, so the Riemannian locally symmetric spaces. So basically, you're looking at things which are not going to be commensurable. So you're looking at the non-compact situation. So you're looking at G is a non-compact semi-simple D group. And so you are taking K to be a maximal compact. And of course, so you're looking at the spaces of the form G mod K, and then you're looking at a lattice gamma, a co-compact, maybe torsion field. Yeah, I don't need but any torsion field lattice. Okay, and then so you would like to know in this context whether the spaces are isospectral or not, whether if they are, sorry, if you have isospectral spaces, whether the lattices are commensurable. This is so the first example of such a thing was given by Andrei, who is also in the audience. Now, Andrei said that there is a context when you get this lattices from arithmetic. So let me explain how do you get arithmetic lattices. So arithmetic. So if you so before so let's G is a group defined over a number field. So maybe let me call this. So G is defined over a, say, number field F. And you can look at the Adele points, GAF, which is the restricted tensor product of G of Fv, where V runs over all the places of F in equivalent. And so you can, so I let G of F tensor R is G infinity. And so what you look at is the compact. So, okay. So let me say KF is a compact open subgroup of G of AF is a compact open subgroup. So then you can define a lattice as follows. So you look at the points, the rational points GF, and intersect it with G infinity times your KF, and project to G infinity. Of course, if I assume G is is a semi-simple group, then yeah. So this gives me a lattice which I'll call it as gamma of Kf. Okay, so this is a finite covolume, but when the group G is anisotropic, when G is anisotropic over F, since yeah, there is no torus which splits, then gamma kf G infinity mod gamma kf is compact. Okay, so these are the lattices which you will be called congruent arithmetic lattices, and anything which is of finite index in them or commensurable to them will be called arithmetic. Okay. So what Alan Reed showed is that he took the example when so Alan Reed, that suppose if the lattices come from a quaternion division algebra, or a totally real number field, and so let me say this quaternion division algebra. So and we say that D ramifies at D splits at exactly one Archimedean place. Exactly one Archimedean place. So then what you get is that the space G infinity mod gamma K infinity is a upper of plane, and so what you get is a compact Riemann surface. And so what the theorem is that if isospectrality, so you are taking two division algebras, implies that the underlying fields are the same and the division algebras are the same. So it's a very nice theorem in some sense that the underlying spectrum recovers much of some of the arithmetic of these spaces. So this was, of course, vastly generalized by Gopal, Prasad, and Rapinchuk. I don't want to. Yeah. This was, so generalized vastly by, and in fact, almost covered the entire situation by Gopal, Prasad, and Rapinchuk. So basically, they introduce this notion of weak commensurability of lattices. And showed that, okay, so they worked in full generality. Yeah. So I don't want to state the entire, all the theorems which they have proved. And showed that isospectrality of the Laplacian on so functions that implies weak commensurability, assuming what would be called assuming Shanwell for higher rank. Yeah. Yeah, because they are congruent arithmetic lattices. D1 is D2, so then the lattices are commensurable. Yeah. Assuming Shanwell in higher rank. Rank greater than 1. So they showed weak commensurability, and from weak commensurability, they deduced that the commensurability. So weak commensurability implies commensurability. In almost all cases where the underlying algebraic group, except in the following situation where the group is of type AN, rank n is greater than or equal to 2. And I don't know whether these cases have been covered in the last few years, and E6. Yeah, except in these cases, if you have lattices arising from other types of algebraic groups, then you have isospectrality, then you will know they are to be commensurable and the groups are the same. Many, even over the number field and various other things you can say. So these are the only cases which are left. Yeah, so I had this thing. So in collaboration with Chandrashil Bhagwat and Supriya Pisolka, what we did was to, instead of assuming isospectrality of Laplacian on functions, we started with a stronger assumption, stronger hypothesis. We assume what is called representation equivalence of lattices. Equivalence of lattices, which is that if I have two lattices inside a Lie group, if this is the infinite generalization of Sunada's condition, that you look at L2 of G mod gamma 1 is isomorphic L2 of G mod as G spaces. I'm again assuming these are all co-compact lattices, so they all break up nicely. So as a discrete, as a Hilbert-Dirac sum of irreducible representations with finite multiplicity. So you can talk about, anyway, you can always talk about whether these spaces are isomorphic as G spaces. And so the point is that when you're going into higher dimensional manifolds, it makes sense to talk about isospectrality not only on functions, but on more general objects. For instance, isospectrality on the space of the P forms and other things. Other like, if I have a Riemannian manifold, that is a reduction of structure group to SON of the tangent bundle, and you can look at various associated bundles to the tangent bundle and look at the Laplacian and acting on the space of sections with respect to the metric, which is with respect to a positive definite metric which is invariant under SON. And you can talk about the spectrum. And you would require, in some sense, if you're looking at higher dimension manifolds, you would try to ask that all these spaces be isospectral if you want to really get back the manifold with this metric. You have to put in more conditions. You don't expect only on functions to work. So, but it's still remarkable that with a bit of Shanwell's conjecture, you can get an answer in full generality. And but the reason for us looking at it is that representation equivalence is a much stronger notion in these cases. And if you know the lattices are representation equivalent, then the various Laplacians, acting on such what would be called natural vector bundles or the associated vector bundles, they are all isospectral. So it's a very strong form of isospectrality. The converse is not known in general except for SON1, that if you know that all the spaces are isospectral, then the representation equivalence is not known. For SON1, it's a theorem of Pesce. Okay, so that is a case. So so it limits out. So what we need to look at now, or look at, if you want to get non-commensurable spaces, you have to look at cases like AN. And so there were some examples which was constructed by Lubotsky, Samuels, and Vishne, but I believe there are some gaps in that. But let me state what we prove. So theorem with Sandeep Verma, which is that, so let me state the theorem. So what, for the theorem, before I state the theorem, let me give the hypothesis which I want. So I'm going to take D1, so F is a number field. And I'm going to take S is a finite set of finite places. I'll give two versions of the theorem, one with this thing. So let me take D1, D2 in general, or division algebras of degree D squared over F. Okay, so what is the assumption on them is that, so D1 and D2, or let me just say for the time being D, so they are split at all places not in S, and remain, it's ramified. That is, D tensor Fe over F remains a division algebra. For places V in S. No, I'm, yeah, no, I'm not. S is disjoint from this. I'm assuming it's split at all the Archimedean places. But yeah, some of them can be refined further, you can, but right now. When I work with quaternion division algebras, maybe I don't need them. But I would still require D is indefinite. Okay, so I want to say D is indefinite. This, of course, implies indefinite, but D is indefinite. Anyway, and I have to say something about the congruence lattices. So the congruence lattices are going to be of the following kind. So I'll just write K, suppose K1, I write it as in general as Ks times. So at, okay, so what is a group? So the group G is, yeah. That is, if I want to say they are non-commensurable, then I will have to say that. But right now, I want to, yeah, absolutely, yeah, right, yeah. Right, but I might also work with the situation where D1 equal to D2, in which case also I get examples of isospectral spaces, which are of course commensurable, but they will not be isometric. Yeah, right, but yeah, okay, but let me, yeah. So G is, so G1, so I will given index, if I give an index, then it is corresponding to the division algebra D1 or D2. Okay, so K is, so these are all contained inside the algebraic group, the finite adels of F. So Ks is just a product of the normal adults D1. Not my phone. In V1 of this thing, right? So this is Ks, where, so I'm taking the full division algebra. So, okay, so this is, let me state one theorem in the first case. I'll state what the thing is. So KIS. Yeah, at the finite set of finite places, it's a full this thing. Yeah, it's a compact group which I'm. And outside, yeah, this is SL1D, the normal elements. DV. Right? So, okay, so let me say here, when, okay, I'll give a refinement later. And what happens is, Ks is contained inside the restricted product outside V not in S, V finite. And there the group is, because it's split, it's kind of SL D of FV. And what I will assume is that so Ki is, I'll write it as a product of KIV, and each KIV I can think of it as a subgroup of SLDFV, the identification. And because these are all inner forms of SLD, it makes sense to ask to put the hypothesis that that for each V not in S, there exists some element, say XV, belonging to GLD of FV, such that say K2V is conjugate x K1V times X inverse XV. So in other words, the lattice structures are conjugate. That is what you would require. Okay. So so this is the hypothesis I'm going to say, and then of course the conclusion is then. So then the space is L2 of say, let me call that G infinity by gamma. G infinity is just product of SLDR or SLDR or SLDC. So G infinity by gamma K1 is isomorphic to L2. G infinity by gamma K. Okay. So is it, yeah? So this is, so of course, as already remarked, so this is the theorem. That is, let me just state one more theorem before talking about this. So there's you can modify it slightly when D1 equal to D2, it's enough to assume, sufficient enough to assume that at one finite place, at one place V naught in S. So I don't need to assume that this KIS or the full group. I just need to assume that KV naught is contained inside SL1D. DFV, which is contained inside GL1D. And I want that this is normal in the full group, normal in it. And my group K is, say, KV naught times some capital K. And here it can be anything. And the other group is, I look at the conjugation of KX by some element X is in GL1D. D of finite. I can take a lattice and take its conjugate, and then I'm saying in that case also, the conclusion is exactly the same, that these spaces are isospectral. But here, of course, in this second example, it is not. They will always be commensurable, but here I'll just come to this. So let me say this is theorem 1 prime. This is theorem 1. Yeah. Okay, so then again, I'll just say that so theorem 1 prime is L2 of G infinity by gamma K. It's isomorphic to L2 of G infinity by gamma K. Okay, so right. So let me just state some few remarks out here. First is that, see, 1 prime is D1 equal to D2. And then I just want to say, I don't need to assume it's full at all the bad places, ramified places. I'm just saying I need to assume that there is one ramified place at which KV naught is normal, and then the lattice can be this. I don't have to assume that KV naught is SL1D V, and also at the other places in S, I don't make any assumption. All I need is one place for which to conclude. The problem is So, but when I'm comparing two different groups, then I'm assuming it is full structure at that place. So I don't have problems about comparing them between two groups at the bad places. Yeah, but at the places away from S, they're conjugate by an element, basically, of GL1D, not of S. Okay. So let me just state the first some remarks. So what about in the first theorem 1 implies non-commensurable, provided your division algebras D2 is not obtained up to an automorphism of K, up to an automorphism of K, or automorphism of the field F. So D2 is not isomorphic to D1 or D1 opposite. And the proof of this is not too difficult. Basically, the fact is that if I look at the spaces, these are products of The symmetric spaces are some products of PGL D infinity in the sense of F tensor R. Yeah. SL1 D of F tensor R, which is a product of, or rather the automorphism group is basically the product of the project of PGL D R some product R1 times PGL D of C R2 times. And then you have the Galois automorphisms of F, and there is a outer action by the outer automorphisms. And since these are all inner conjugation by an element of this space, basically, if you look at the algebra generated, then the rings will be the same. Okay, so that's not too difficult. So if you assume you have to produce examples of division algebras, which so that D2 is not isomorphic up to a Galois automorphism or D1 or D1 opposite, but the Galois automorphism preserves the places which are lying over each rational prime, and then it's and by class field theory, you know the invariance at any finite place V is of the form A by D, where 0 is less than equal to A less than D. So you're looking at numbers between 0 and 1. So the opposite algebra is invariant minus A by D. And so you can always take many places for which this condition of not satisfied. A has to be prime to D at the places S. Yeah. AV D equal to 1 for V in S. Yeah. Right. So that you get a division algebra at the places, at other places it's AV is 0. So the non-commensurability is, so you can produce lots of examples. Second thing is that this example, in some sense, it generalizes Veneras, and for theorem, so as, of course, when DI is quaternion, DI is a quaternion division algebra, then of course I will take the theorem 1 prime was proved by me long back. I proved it maybe 2007 or so, something like that. And it kind of it generalizes the Veneras example. So what Veneras does, she works with quaternion division algebras, either or real quadratic or an imaginary quadratic field. And also she has to work with lattices which are full level structure. Whereas here you can avoid those examples. Her proof is geometric. It uses Eichler's way of counting elements, getting at the length spectrum from looking at elements in the lattice on a maximal order. So what the proof I was using was this was more automorphic forms theory. But before that, let me give my motivation for why you're looking at spaces of this form. So the motivation for looking at the example, So it arises from this Shimura's theory of canonical models. For Shimura varieties. So what the spaces which you are looking at, so when I work with, for instance, suppose f is totally real, and maybe assume not, so you can get at situations where the varieties which you are looking at, J infinity mod K infinity by gamma K, they acquire a algebraic structure. They are complex varieties. I'm not exactly saying in what all cases you are getting, but you can work with, say, for instance, quaternion algebras or whatever it is, and say which is like a Shimura curve, where it is in the examples of Alan Reed, you are taking a quaternion algebra, which is, or more generally, you can look at vector spaces over a quaternion algebra, which gives rise to symplectic groups at infinity. So what happens is that these are complex varieties, and they have a natural models, what are called canonical models. Defined over, I can assume that the reflex field, defined over the reflex field, which we can assume in some cases equal to f. So what I'm saying is that you get examples of the Shimura varieties, which are in this case connected Shimura varieties, have models which are defined over the reflex field, which we can take it to be f in some cases. And what Shimura describes is the effect of Galois conjugation. Effect of Galois group f bar over f, conjugation on the variety. It's defined over some, so these varieties are defined, so I should say, these varieties are defined over an abelian extension of or f abelian, the maximal abelian extension. So it defines what the action of the Galois f abelian over f conjugation on this space. And the point is that you have the ideals AF star, you have mapped to okay. So what you do is so this is the reciprocity map, and so I can look at in this case GL1D of ideals, and you have the reduced norm to AF star, and here you have the reciprocity. And this, so what happens is if I have an element X, I go to an element sigma X here. So if I have the variety xk, and if I conjugate by sigma X, that he's saying is nothing more than xkx. So this is Shimura's one of the reciprocity laws, that the Galois conjugation of this variety, which is defined over some abelian extension of f, is really an adelic conjugation. And what one of the conjectures or expectations I was having based on examples of Reed and Sunada and other things is that the spectrum and in some sense the arithmetic should determine each other, which is stronger than saying that they have to be in analogy with each other. So what happens is, if you assume that the Galois conjugation preserves arithmetic, which is whatever it is, it does preserve the arithmetic, then you should expect that the spaces xk and xkx have to be isospectral. So that is what was the initial motivation in proving this theorem for quaternion diffusion algebra. But sorry, how much time I have? Oh my God. Only 1 minute. Okay. Sorry, I should have. I've not said anything about the proof at all. So the proof both in the quaternion division and in higher rank, it uses a trace formula, but more generally what is called the stabilization of the trace formula. So which of course, for the case of D quaternion, it was done by Lebesgue-Langlands, and in general, this is of course the work of Novochov and Wolfsberger, Arthur, and many others. Yeah, there are too many people which is going on because Wolfsberger, Arthur, of course, Langlands, Shellstad, and Kortwitz and others. Okay, so it uses the full force of the stabilization of the trace formula. What happens is, although the Selbert trace formula works in the anisotropic case, it's not possible. It is not true that, at least in the case of SL1D, that the multiplicity of any representation pi is equal to the multiplicity of pi x. So this is not true. And at least in SL1D, for instance, the counterexample is when pi is what would be called a CM form or a dihedral representation. Here the multiplicities are not equal, with which it occurs in the space of automorphic forms on SL1D. And so what Lebesgue and Langlands do is to give a formula for the multiplicity. It's like, so here what happens is it's like the discrete series has a D plus minus. So when I look at SL2R, but when I look at GL2R, these representations form an irreducible representation of GL2R. But when I restrict to SL2R, they form two components. And this is the problem which occurs when, anyway, yeah. So the proof requires a stabilization of the trace formula. Okay, so what, for the SL1D, what I did is to use the formula for the multiplicity, and which is a product of signs, and I needed this one place V0 because it's a division algebra, which is the representation is like a discrete series at the component, and I just took the other component such that the signs become 1, so that the multiplicities remain the same, but the normality ensures that the invariant vectors are also the same. And so that was the proof in the SL1D case. But in general, we need to use a full use of the stabilization of the trace formula. So what happens is, if I look at the trace of a suitable function f infinity tensor, the 1k, k1, so I need to say this is equal to trace of f infinity tensor 1k2, where f infinity are smooth compactly supported functions, and 1k1 and 1k2 are the characteristic functions on this. So what this says is the stabilization writes it of this formula as something which is what is called stable on the quasi-split group, which is, so let's call that G star, plus some error terms which are coming from what is called the elliptic endoscopic. So basically, endoscopic groups are kind of centralizers of elements, and you want them elliptic in the sense they share an elliptic torus with the group G, elliptic endoscopic data. So the main point of a proof is to say that when the image, when I write it in terms of this form, then out here this becomes 0. So it gets reduced to whatever is called the quasi-split case. Okay, and that these two forms, even if they are on different algebras, different groups, they give you the same stable integrals, is because stability in D star or in SL1D amounts to conjugation by D star, or in SLD, it's conjugation by D star. So the stable integrals, when you conjugate, are still the same. So out here, these are equal, but here, now that will take a bit more time to explain, and I don't think I'm completely comfortable with it to give an immediate explanation. But the point is, so these error terms, and there is a transfer of functions which is defined in terms of Langlands-Shellstad transfer factors, and what one has to say is that they vanish. So that is what is the proof in this case, which is yeah, I think, yeah, sorry, I'll stop here.
All right, do we have some questions?
Yeah. Thank you. So for theorem 1 prime, you have this assumption at the place V0.
Yeah.
What if you remove this assumption? And you just
I don't know.
You don't know. You expect the answer to be yes?
I would, if I believe that the arithmetic should imply the spectrum, then of course I expect it to be yes. But I have no idea what should happen. For instance, if, yeah, right. I don't, I'm not able to, yeah.
How about the other types? So
sorry, E6.
E6 and D.
D2, no, I'm not, I don't have this thing. But he was also raising things about outer forms of AN.
Yeah, whenever you have H1 back from the full automorphism instead of the I. So the Hasse full O.
Thank you.
For E6, but for something interesting, then even you have problem.
Sorry, I thought D2n plus 1 is a problem. Or D2n plus 1 is a problem, or D2n is a problem? I thought it's D2n plus 1. But maybe, yeah, but maybe you're right. One of them is a problem. The other one is, yeah.
The center in one case is G mod 2 direction.
Okay.
And in the other case, has something to do
With that, okay.
for unitary,
Yeah.
you have a
Yeah.
then can say that
Yeah, right.
G and G prime are not isomorphic.
Right.
But at all finite places.
Yeah, but I think even for in this case itself, division algebras itself, if I don't put this kind of normal assumption, I don't know a way of doing it. Yeah, so even with the stabilization of using the full force of the stabilization, we use heavily this assumption. This assumption is used heavily. See, when I say that the error terms vanish, what is shown is out here is that at this point, the components, there the things vanish.
So for unitary group, your proof is not work.
I don't know, unless I have no idea. I have no idea. Maybe one should ask the, Sandeep should be. No, Sandeep Verma should probably. Do you think it?
More distance.
Yeah, naively.
Yeah, naively it doesn't work, but it's a very interesting thing to think about. Maybe.
Yeah, you know, I get the thing, but yeah, right.
Group is not globally isolated.
Right. No, yeah, no, that's what, but yeah.
One would expect that in that case.
Yeah, but yeah.
I
So,
mean, that's what Harris and Taylor say.
you mean the
You know, Harris and Taylor.
yeah, no, but see there, I suppose the local Langlands, sorry, the Jacquet-Langlands has been done in this kind of cases by Badiluska. So I think he has completed the Jacquet-Langlands for inner forms of Badulus.
Only for inner form.
Yeah, inner forms.
Yeah, so for outer form.
No, but yeah, right. But you can for in the Lubotsky-Samuels-Vishny paper, the use of Harris-Taylor can be replaced by the Jacquet-Langlands of Badiluska. The generalization of Jacquet-Langlands to inner forms. The mistake is slightly more complicated. What happens is, see, when you use the Jacquet-Langlands, you have to work with the adjoint group, right? And then it's a union of connected components. And the connected components are all of the form Kx, conjugates of Kx. Okay, so what happens is, although the Jacquet-Langlands says that the sum of these spaces are isospectral, and the number of components by a class group computation you can say is equal, you still have to say that the individual components in both the spaces are isospectral. And that's precisely what this theorem achieves. That the conjugates, what we call the conjugates by elements of GL1 or the adjoint group, those lattices are all isospectral or representation equivalent to each other. So this has to be proved, and that is not there. And that requires really the full force of stabilization. You can't do without, because of this fact that the multiplicity of pi is not equal to multiplicity of pi x.
So they have done some work on it.
Okay.
But I asked them to do this.
Yeah. Yeah, no, the proof. Yeah. Yeah, so the main thing is to observe that the condition at a specific place V0 means that these error terms, the endoscopic terms, which are not equal to the quasi-split, they all vanish. And that uses a inversion formula of Arthur, which is a formula for the inversion of this Langlands-Shellstrad transfer factors. So it is some things which
doesn't work for unitary.
No, I think it works in full generality. I have no idea, but the point is this: I need this very special assumption at this place V0, some kind of yeah. No, Arthur's paper is very general, so I'm not the same.
No, but can't we do the same trick with unitary?
I have to look at it. I have not really looked at it.
Thank you.
But I think I will give it to, yeah, I really don't know. I can't say. Yeah, for the inner forms, I can, I don't know. For the, yeah, no, I can't say. I don't have.
Okay, so perhaps we should take the coffee break and thank the speaker again.
Okay.